Yep. And
Tommy. Yep, so we didn't plan it today.
Okay.
It was dumb.
Back to second round, did you end up making it to the game at all?
No, and it was pouring down rain.
I know it wasn't a fun one to sit through, but you did miss a good game.
That's what I understand.
Me too, dude.
Why is it
So
nice?
did you do well?
I was alright.
You were not in the box score.
What's that?
You were not in the box score.
Oh, was that? I mean, I didn't
You
have.
did not make it to the stat sheet.
You only had 15 tackles. It's okay.
Oh yeah, no, it's fine. I mean,
No, that was awesome.
it was.
When I saw that
crazy.
you guys won, I was like, way to be.
It was a crazy game.
Why does it say HDMI?
Yeah, boys.
So now you have lone control of the top spot in the conference. Hey,
Now we just have to win out. That's easy, right?
what happens after that? So you just like win conference and then, whoop.
Go to playoffs.
Oh, you go to the playoffs if you win conference? Okay. I'm not talking about playoffs? Playoffs? Let's talk about playoffs.
All right, Jim.
Playoffs?
So did everybody get my email?
What does the company do?
No.
They're like for Lilly Drug?
They are a branch of Lilly,
So they do chemistry?
but they do animal products instead of human products.
Animal hair.
So, and they're essentially looking for internships for this coming summer, or people to be hired. Yeah. And they're trying to find out how many are gonna show up. So they're gonna be 5. They're doing the thing Tuesday night from 5, tomorrow night from 5:30 to 6:30, sort of free pizza and learn about the company. And then if anybody who, you know, you give him your resume tomorrow night, then he will look through the resumes and decide who he wants to interview, if he wants to interview anybody, and we'll arrange interviews then on Wednesday. So, I mean, you know, it's, the equipment it's all mechanical equipment that they use to process the drugs and stuff, so that's why they're interested in mechanical engineers, and they're interested in chemical engineers from the standpoint of doing the batches of stuff that they make. So those are the 2 disciplines that they're really looking for. We don't have chemical engineers, but we have chemistry majors, so he's willing to consider chemistry people. So I would hope that we could at least put together a few people that would be willing to, you know, go to the information session at least and then find out about internships. But if you don't, then no one has any excuse for saying, oh, I couldn't find an internship next summer. So I do not want to hear that from anyone who does not participate in this thing. So. But like I said, I need to know ahead of time though. So if you are going to go, let me know by the end of the day so that we can,
By the end of the day today?
by the end of the day today, because he's coming tomorrow morning. And I'm supposed to meet with him tomorrow morning to sort of give him a better rundown on, you know, what the engineering program is like here. And then he'll meet with everybody. He's doing the internship fair down, I assume it's down in the atrium, in the afternoon tomorrow. But then doing his own private sort of information session in the evening with pizza.
Okay, so there's an internship fair in the atrium room?
Yes.
That's not for engineers?
Well, because the engineers have their own, you know, we do our own career fair or whatever, you know, 3 weeks ago. And
Yeah.
so that is primarily where all the engineering positions are available.
Okay.
So there's not so much, I mean, there may be a few that have, the reason he's coming now is because he wants both chemists and engineers, not just chemists, no, not just engineers. So he wanted to do it at this thing because that's when everybody's available. That makes sense? So.
Do we ever have like a physics engineering kind of fair? Because it
It's
seems
the-
to be like,
we did it with computer science, that was
yeah,
the.
it just seemed like there's a lot more computer people.
Yes, we are not as good as we need to be about incorporating engineering and physics companies and opportunities in that. And I'm working on that, but I'm new, relative,
Yeah.
so. So Cummins engine was supposed to be here,
Yeah, I was
and they
waiting
blew us
for
off. I don't know what that was about. So,
I was kind of waiting.
yeah.
But
So, anyway, so this is one. I'm also working on a relationship with a biomedical company, because we have a few people interested in biomedical engineering, Depew up in Warsaw. So a lot of things like that. But, as I say, you should at least take advantage of the opportunities you do have, rather than waiting for ones that may never materialize. Okay, any other questions? So far, I've had 0 people reply that they'll be attending. So I'm going to be really embarrassed if he gets here and I say, we have no engineers, but thanks anyway. Okay. In which case, it's going to be even more difficult to attract more physics and engineering positions when we don't even respond to the ones that we do.
So we should come, so.
That's what I'm saying.
It's okay, I'll come. There you go, one response.
But you have to bring your
Resume.
resume. Okay. And it won't kill you, even if you don't want to go work for Alamco. You could, it doesn't kill you to resist the process.
I won't be able to make the, is there a way I can maybe just give him my resume?
Yeah, like I said, he'll be here all afternoon down in the atrium, so you can
Maybe I
still
can
get
stop
him
by.
the resume down there. Okay, combined loading. So we added pressure vessels on Friday to our sort of list of things we do with beams. But now for combined loading, we're really primarily focusing on beams. So we've defined two kinds of stress, two kinds of loading that can exist somewhere in a beam. We have normal stress and shear stress, right? Sigma and tau. What kind of things do we have that give rise to a normal stress? What kind of loadings do we have that can give rise to a normal stress at some point in the beam? This is sigma, and this is tau. So what kind of loadings give rise to a normal stress? How could I load a beam? What kind of load could I apply to a beam?
Is that like a hanging load, I guess?
Okay, so we have a horizontal beam, let's say, but okay, a hanging load in a vertical configuration would be an axial load,
Yeah.
right? Because you're applying it along the axis. So we have an axial load. What are the kind of configurations will give us somewhere in the beam a normal stress?
Whatever's perpendicular to axial load.
Whatever's
Because if you could have normal stress going this way, but you could also have normal stress in the segment going down.
So, yeah, we didn't talk about that. We'll explain why that's not the case.
Okay. You
What else gives rise to a normal stress? Ooh, what was that?
bending.
Bending. Bending in Y, so if I take this thing and do this, this is what you're actually talking about. If I do this, or if I push down on the beam here, then I'm creating a bending moment. And that bending moment is what creates the normal stress.
Okay. So I guess what I said before would work, but I just didn't work right.
Yeah, well, I know what you were trying to say. What you were trying to say was not really correct, basically. Because you have to have constraint in this direction. So if I'm gonna load a beam and create a normal stress this way, then it's got to be constrained in that direction.
Oh, yeah.
So I'm just squeezing it. I'm not really, right? It's not a beam, right? So in a beam configuration, I create a normal stress in this direction by bending it. So I bend it, the bottom's in compression, the top's in tension. Okay. What else? Bend it in Y. Kind of tried to give you a hint there.
You meant Z.
Could bend it in Z. Right. Bending in Z. So we bend it this way or that way. And the front or back would be in compression or tension. Right. Do we discuss anything else that gave rise to normal stress? Answer's no, okay. Let's move on to shear stress. What can we do that creates a shear stress in this beam? What have we talked about that creates a shear stress in the beam? Twisting. Okay, a twist, so torsion.
Just a vertical load.
Right, a shear load. Right, so we have shear in Y, and similarly we would have shear in Z. So we could load it like this, or we could load it like this.
Yeah. Didn't we also have a shear stress in bending?
So the applied shear load will also create a bending moment.
And then that's where the stress.
And the bending moment gives us a normal stress. But the shear itself gives us a shear stress. Right, so we have both a shear stress and a normal stress created by the applied shear load. But we don't necessarily have to have an applied shear load to get a bending moment. Right, so this will create one of these, but one of these doesn't create one of these. Okay, does everybody remember that now? So we have three things that can give us a shear, and we have three things that can give us a normal stress in our one-dimensional, well, nominally, so I mean, it's three-dimensional, but it's axial, in an axial beam, yes.
I had a quick question. It seems to me that, I mean, obviously my assumption is wrong, but I don't understand why I think this bending would cause both the shear and the normal stress.
So bending itself does not cause, so it depends on how you define bending. We'll check again. So if I bend something, if I apply a bending moment, remember it's like putting a screwdriver in and turning it, right? So yeah, there's a force couple and there's actually some shear maybe that happens right there. But if you think of that as a small point in the relative structure of the beam, that bend doesn't create itself a shear. What happens is there must be some kind of shear reaction. The beam is going to be straight, and that shear reaction then, distributed along the beam, creates a shear stress. So in the mode of analysis that we're using, the bending moment doesn't create the shear, it's the shear that responds to the bending moment that creates the following.
Yeah, so.
Okay. So let's take an easy one first. 822, up there at the top. We have a clamping vise. We have two pieces that are sort of form this loop. And you turn the screw, and it tightens the member. That's interesting, actually.
That's an interesting clamp.
Yeah, that actually doesn't work the way they've drawn it. So the screw actually has to reverse its threads on the other side in order for both of them to clamp. Either that or the bottom's got to be just some kind of, you know what I'm saying?
It's gonna be all the way up against the.
So otherwise I'm just screwing through the whole thing, right?
Yeah.
So you normally have a point in the center here where there's no threads, and the threads on the top are the inverse of the threads on the bottom. That's normally the way that would work. But nonetheless, so you screw it and it tightens it down. So the question is, if this clamp exerts a compressive force at C and B of 180 newtons, right, it's squeezing the wood, pushing down on the wood with 180 newtons. What's that?
Well, it does work as soon as the collar touches segment AB.
What do you mean?
So when the collar, so if you're screwing in when the collar touches at, you know, where E is, once it touches the metal of the clamp, then it's going to just
Only if that
pull.
collar is rigidly attached to the shaft. Right,
I
the
just-
collar's not
I
rigidly
just-
attached
I
to the
just
screw.
screwed one piece.
Well, I'm assuming it's not because there's still threads below the collar. See what I'm saying?
Oh, I'm talking about the apparatus where the bar is going through that you would actually turn.
Right, this thing here, right? That collar,
Not that collar, the down.
this?
yes, once that touches.
Yeah, but it's
there.
not, in this configuration, then it would not be creating the clamping force, because it's still threads.
It wouldn't screw in and then pull,
It would eventually, it might eventually, but actually,
In this picture, it's not.
yeah,
because
this
it's not-
picture is not clamping,
Because it's not up against the car yet.
Oh, okay.
that's what I'm saying, so they've got it kind of long. Anyway. Creates 180 Newton clamping force, okay? And then we have a cross-section AA, which is pulled out in the cross-sectional view there on the left. And we are to determine the maximum compressive stress in that cross-section. And it says the screw EF is subject only to a tensile force along its axis. So what do we do? And this is the easy one. What do we do?
Blake?
Oh, maybe we could do a free body diagram
Of what?
of, the cross-sectional face. So we want to do
So we do a free body diagram of the square,
that. So then you'll have two forces compressing off top and bottom.
Well, I think we need to take a step back from there first.
Shouldn't be the picture of just the clamp.
Just the clamp? What member of the clamp or the whole thing?
Just the whole thing.
Okay, well then, if we do the
Yeah,
whole
it's
thing, we
just-
have
in there,
no,
you missed it.
we have no forces. Right? Everything's an internal force. Or an equal and opposite force. I don't think you want to do the whole clamp.
Okay, now.
Do the whole clamp, because there's, what external forces are acting on the clamp?
Zero external forces.
Well, yeah, there's a force upward at C and a force downward at B, and those two are equal and opposite, so there's no net force acting on the clamp. So that would not be the piece we want to use.
Could we just do either AEB or AFC?
Okay? Which member is cross-section AA a part of?
AFC.
So what piece do you think we ought to do?
AFC.
AFC, probably a good choice. Okay. AFC. There's AFC, okay?
No, that's the problem.
All right, what are the forces acting on AFC?
There's that force from the piece of wood and then a reaction force from the clamp.
So we have a force here, we'll call that F sub C, and a reaction force from the clamp. What's the reaction force of the clamp look like, from the clamp look like? What point is that? At what point is that reaction force applied?
Gonna technically have two, right? One at F and one at A.
Okay, what you got at F?
Should be a force pushing down at F and a force pushing up at A.
Everybody happy with that?
Mm-hmm.
It's kind of a constraint is A. Pin, what kind of a reaction does a pin have?
Don't like shear stress, don't stress.
No.
A pin it'll also have a force in the X direction.
Right, so there would actually be two forces there. Right, there's the potential for two reaction forces there. Right?
Yeah.
Okay. Okay, so, do we know what any of those forces are?
We know the 180 Newton C.
Okay, this is 180.
So we know F plus A must equal 180, right?
F plus A?
Or F minus A or A minus F.
So F minus A, probably.
F.
So you're saying the sum of the forces in the y direction equals AY minus F plus 180 equals 0. So that AY is equal to F minus 180.
Wow, you just said that so well.
Okay.
I can't get it.
So that's a good statics analysis, right? So, but that's two unknowns.
So we do a moment about either A or
What are you probably going to do the moment about?
A.
We're going to do the moment about A. Sum of the moments about A equals 7. 0.07 meters times 180, right? 0.7 over, 180 out, it's positive moment, out of the board, minus F times, or what is that, 30? 30 times F, that equals 0, therefore F is equal to, oh, 0.03. Oh yeah, oh no, sorry, my bad. So F is equal to what? 1260, 5.3, 420. 420 newtons. Okay? So now we know AY is 420 minus 180 is 240. Okay, we found the reaction forces. Now what? I should know. Remember to draw my section that I'm concerned about. So what do I do?
So now we need to find the stress.
Now we need to find stress. Okay. What's the expression for stress?
Force or area?
Force divided by area. Do I know the force acting at section AA?
Yes.
What is it?
240.
It is 240. Right, so we're doing a section here, so we do a second method of sections down here. Is AX, it is experiencing an AX as well? AX is 0, because the sum of the forces in the x direction is 0. So there is no AX. Therefore, there's no shear, internal shear at this point. Therefore, there's no moment at this point, so I don't have to worry about the bending contribution to the normal stress state. See what I'm saying? Otherwise, if there was some kind of an x component, I would have to then integrate that x, that shear component, up to here, right? Because the moment is the integral of the shear. Find out what the cross-sectional moment was, and then we use that moment to calculate the normal stress, bending. You guys remember this stuff? Do you have any recollection of what I'm talking about? Wah, 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 right? Okay. So because there is no AX, I know that there is no shear component or bending component at this cross section. Since there is no bending component in Y or Z, all I'm concerned about is the axial load. That axial load then is 240 newtons. What is the area?
The area is
15 or 0.015
squares.
1.07 megapascal. Okay? That's the easy one. Because all we have is normal stress. You can see the next one's going to be a little tougher. It's got a drill. It's got all kinds of weird parts and stuff. It's good. Okay? So what we would have done, if there had been some kind of a bending moment, an AX, right, some kind of a shear force, is we would have to then calculate what is that, the moment at the cross-section of interest due to that shear. That moment of the cross-section of interest would give us a normal stress. We would have to add that normal stress to this one. So all we're doing is superposition of these three pieces to find the normal stress, and superposition of these three pieces to find the shear stress. Okay, so you have to analyze each one independently, and then hopefully at the end you can add them all up. Does that make sense? Okay.
Got a good question.
Yeah?
If the block of wood supported, like, I guess, some static friction, could that support a X component of force at point A?
So there would have to be a shear in the wood. In other words, the top block would have to be being pushed forward while the
But it
bottom
couldn't
was
be-
pulling backward because there'd be no net force on the thing. Right? There has to be no net force in the horizontal direction. This is an isolated system. Right? So there can be no net force acting on the whole thing. So if B, or if at C it was pushing to the left and B was being pulled to the right, so that I was taking those pieces of wood and going like this, then yes, there could be a moment. Okay, and I would have found it by taking that moment and applying that as an applied force, that frictional force as an applied force here, mu times 180. And then I would have had a mu times 180 here, and then I would have integrated that mu times 180 up to my cross section to find the total bending moment at that point. Make sense?
Could we have also gotten that, say, the clamp wasn't completely perpendicular with the wood? That would also cause.
Yeah, so let's move on to another real problem instead of thinking of what. That's gonna be a problem there.
What if we had?
I have some questions.
Yes?
No, I don't.
Okay. When I was in kindergarten, all right, the drill is jammed in the wall, and subject to the torque and force shown. Determine the state of stress at a point A on the cross-section of a drill bit at section AA. So they've given us a picture of the drill and the cross-section, and they said point A is the top center of the drill bit. That make sense? We're going to find the total stress state on the top edge of the drill bit.
Is that the AA in the picture, is that the cross-sectional area at the bottom?
So the circle that I've drawn here is section AA,
Okay.
which is a cross-section through the drill. As I'm sitting here going at the drill, this is a cross-section, and we're interested in that point at the top of the drill edge. Okay. All right? So, where should we begin?
Free body diagram.
Of?
Well, we have to include the force of the arm.
So what are we doing in free body diagram?
The drill.
The drill, good choice. Notice how I just cut you off right there when you said the drill.
The drill. I was gonna say drill as a whole.
Okay.
I was gonna say that.
Sure, you would.
Okay. So we've effectively got this. All right, that's my free body, that's my drill.
Okay.
Dimension of 0.4 meters that way. And now let's shorten it up so it looks like it might actually be 0.125 meters this way. And down here, we have an applied force, it says a 345. Yeah. We have a 345 triangle. Applying a force of 150 newtons. The drill itself is applying a torque up here, whoa, of 20 Newton meters. Okay. I think that's all the, is that all the pieces of the free body diagram? I should label the points. Does that have a point? Nope, let's just call it C and D for convenience.
There should be a reaction force at C.
So there should be some reaction at C.
Two reaction forces.
So let's see what all we have. What kind of a constraint is point C?
Are we considering this drill to be not twisting or not being moved? Or
So
something?
it is a static configuration. Right. I mean, the drill is presumably turning. Right? We don't know if it's actually able to cut through the material or not. Right, so maybe it's jammed in so that so hard that it's not turning. The drill's going. Right.
Okay, so that's bad.
All right. Any other things I need to include? So I've got a reaction force. What reaction forces do you want me to put at C?
I'd say one going to the right on the x-axis, and then one going down on the y.
Can I draw it up on the Y and then we'll spin?
Okay.
Yeah, that's fine. No, that's fine. I'll do it down on the Y, that's fine. See Y. What kind of a constraint is that at point C?
What's that? Kind of constraint?
Yeah, what kind of constraint is that location?
Bone in the frame on this one.
It wouldn't, it'd just be like it's gonna be constrained in all directions. Is that what you're asking?
Yeah, that's what I'm asking. It can be constrained in all directions. Right, so there can be also a Z force, right, out of the board. There could be a bending moment. There could be a torsional moment. There could be everything at this location, right? So, which of those do I really want to include? I've got CX and CY. Are there any others that I want to include? Bending in the Y, bending in the Z, or moment about the X, or force in the Z?
Probably want a moment about the X. It's a reaction moment.
So some kind of a reaction moment. So call that a torque, right?
Yeah.
Is it going to be in the same sense as that or opposite sense of that?
Opposite.
Right, so it's probably going to be this way. Call that torque T. Right, because that's a moment about the axis, which we typically call a torque, as opposed to bending moments, which we call moments. Right, this is torsion, that's about the Z, and the X and Y here are bending moments. Okay. So, what else? Any other things? Any bending moments in the Y or Z directions? Do I need to worry about? Or force in the Z? Should I worry about a force in the Z?
I don't think you need to worry about a force in the Z, but you could
Why
draw.
not? Why would I not worry about force in the Z?
There's no forces acting.
Right, there are no forces in the Z direction, so there'd be no reason to have a reaction in the Z direction. Right? Are there any applied moments in the, bending moments in the Y or Z direction?
There will be
In which direction?
the
Y direction.
No, in the Z.
In the Z. Right, Z is out of the board. This thing, unless it happens to go right through point C, which it doesn't, is going to create some kind of bending moment in the Z direction. You see that? There's the potential, at least, for a moment in the Z direction. But there's unlikely to be a moment in the Y direction because there's nothing here that bends it in the Y direction. Okay, so there's going to be some kind of moment the z direction. Okay? So this is a torque whose direction I have shown by pointing it that way. Right? So I put this little wrappage thing around it here to show that it's a torque, but in reality that vector defines its direction, whereas the moment in z is defined by that vector. See what I'm saying?
Yep.
Okay, so it's a little confusing why this and this are both there. This is actually the vector, technically that's the vector, but I draw the little loop around it to show that it's a moment vector as opposed to a force vector. Okay? All right.
So the reaction forces at C or A, wherever the drill bit's going in.
That's
Reaction
point C.
force-
Point C. Point C.
Those don't like represent the moment that's being applied, or like.
No, that's just a force upward on the drill or a force downward on the drill. Okay? Because if you think of it in terms of, if this were a pin instead, it could exert those forces, but it could do nothing to twist the drill
Yeah.
if it were a pin.
But this can.
But this, because it's an embedded, right, it's a rigidly fixed member, it can apply all the different dimensions. And the only two we don't care about are moment in the y, because that would require a z force,
Yeah.
or an applied moment, which we don't have, right? And force in the z. Because we have no z forces, we can ignore the z forces, and we can ignore the moment in the y. Okay? Okay. Whew. So now we have this very elaborate, it started out as a very simple free body diagram. It was just an L. But now we have this much more elaborate system. So what are we going to do? We have no forces. So how many forces, how many things are we going to sum? What are the things we're going to sum?
Well, that's 6 equations.
No, we're not going to have 6
Oh,
equations.
5.
Nope.
No, 3, 4,
2,
1,
We have-
0.
Wake up, boys, come on.
Imaginary,
We have
complex.
Y. We have 4.
We have 4. We have no z, and we have no moment in the y. Those are the two things we don't have reactions for, right? So we have 4 equations because we have 4 unknown reactions. Right, we're going to have 4 equations.
What
All right.
also floats on water? Churches. Gravy. Very
What?
small rocks. That's how I felt like. Monty Python. Calm down. Okay.
Well, a duck floats on water, but I don't remember the churches floating on water.
Yeah.
All right. Okay, anyway, so some of the forces, and what do you want to do first?
X.
X, because we're alphabetical like that. What are the sum of the forces in the x direction?
They are reaction force of Fx.
Or cx, as I've drawn it up here.
Cx, and then our applied force in the x direction, which.
What are the rules for 3, 4, 5 again?
36 point.
What?
The rules for the 3, 4, 5 triangle
Is that they scale in proportion to 3, 4, and 5.
also be 4 times 1/4 of 150. So
It would be 4/5 of 150. It's 120. See what I'm saying? This is 150, and the multiplier is 30.
oh, okay.
So this would be 120, and this would be 90.
Gotcha.
Whew, okay.
I'm struggling today, boys.
Riding the bus. Okay, is that positive or negative?
That's negative.
Okay.
So we just can go to the y. CY minus 90.
Are we happy with CY minus 90?
And that's because you multiplied 3 over 5 times 150.
All right, I would actually say it's minus CY plus 90, or 90 minus CY, because the CY, the way I've drawn it, is negative, right? 'Cause the y-axis is positive, x-axis is negative. Technically speaking, they've drawn the x-axis to be positive as well, but the way that I've drawn it, I'm drawing the x-axis positive. Doesn't matter. CY equals 90 newtons. You know, in that direction as I've drawn it on the board. Okay. Okay, what next?
Some of the moments about the x-axis.
Some of the moments of the x-axis equals, what are they?
We have our applied, or our torque, T,
T,
which is positive.
the
And
way
then,
we've been doing it,
Minus 20.
yeah, minus
yeah. So T equals 20 Newton meters. Okay, got one more unknown.
Then we, some moments about point C in the Z direction.
So the moments in the Z direction at C equals what?
4 times
0.4, 0.4 times 90.
120 times
Is that positive or negative?
That's positive.
Okay.
And then we have 120 times 0.125, which is negative.
Because that one's applied down and to the left, so negative.
And then we have our reaction of MZ.
Did I draw my MZ positive or negative?
Negative.
I drew it as negative. Okay, so what do we get for MZ?
$21.
21 Newton meters. Okay, we have all of our reactions. So, what does that do for us? What are we trying to find again?
The stresses, yeah, the stresses at A.
Okay, what kind of stresses?
Shear stress. Just the state of the stress.
So what does that mean?
What kind of stress it is? We're trying to figure out what kind of stress it is.
No, we're trying to figure out how much it is, but we're trying to do both shear and normal stress. The state of stress is represented by these two pieces. We have both normal and shear present. Okay. So what's going to give rise to a normal stress?
Our compressive force.
Okay. So the normal stress is going to be the compressive force. Is there anything else that's going to cause a normal stress?
Bending.
Stress due to bending. Right? We only have one bend. We only have the bending moment in the Z. We don't have the Y. So we only have to worry about one bending stress. So now let's find out each of those two pieces, add them up together, easy peasy, we're all done for the normal stress. So what's the compressive stress at point A? Right here. What's the compressive stress at this point?
Would it just be 90 times divided by the area? Cross-sectional area?
90.
We're looking for bending
Not
or
applied.
compressive stress?
X, here, let me draw mine. That's for that.
Oh, yeah, it'd be 120, sorry.
Right, the 120, it's the X piece, right? That's the normal axial load,
Sorry,
all right? So we have 120 is the total force divided by
R squared.
pi r squared. What is pi r squared? Well, we probably should have calculated that first, because we're probably going to need area for a couple different things. So it's actually helpful in these situations, once you get the free body diagram done, to come back and calculate, oh man, calculate the fixed values, the values that are uniform for everything. So those fixed values are I, J, and A. Area, well, not in that order. Area A, moment of inertia I, and J, the polar moment. Okay. So A is going to be pi times 0.005 squared. That's going to give us, that's the compressive force or the axial stress, whether. That's going to give us, I didn't give the individual pieces. All right, never mind. We'll leave that one empty.
Do you want it?
No, it's okay. Well, that's all right. You got it?
Yeah, I've got, okay, 15, I got 1527887, which is gonna be 15 times 10 to the 5th.
1.53 times 10 to the 6th.
Yeah.
All right, that's 1.53 megapascals. Right? Okay. What about the bending stress? How do we calculate the bending stress? Stress due to bending at point A. Everybody remember that one? In a couple weeks? Stress due to bending. If you had your book, you could open the inside front cover for all of your equations. It'd be right there for you. Unless, of course, you bought an illegal copy of a foreign book.
Please, the stress due bending in the X
Well, in this case, it's the moment in the Z direction, but nonetheless, doesn't matter.
would be M times Z over IY
All right, so it's My
times Z
over.
over.
So it's My over Iy because it's moment about the Z axis. It's M sub Z I times Y over Iy plus M sub Y Z over Iz. Right? It's the moment about the Z axis, but the position at which creates the most stress, at which it creates stress is on the Y axis. So this would be M sub Z times Y over Iy plus M sub Y Z over Iz. We did mention that briefly. There was one, that was on the board at one point, but it was just, we kind of.
Yeah, I have it written down right here.
Okay, but it's M sub Z times Y over Iy.
Oh, I have it written down wrong. I have M sub Z times Y over IZ. So I need to-
Over Iz. You got Iz too?
Did you have IZ? Very good chance I wrote it down.
Okay, okay. Well, I may have written it down wrong originally as well. But the moment we care about here, well,
Inertia.
yeah, okay, so you're right, it is Iz. It's the moment about the Z axis. You're right, which is this axis,
Yeah.
right? You're right. M sub Z, Y over Iz.
Well, you were right before.
Whatever. Mutual Admiration Society's over with. That's it. Okay, we got MZ. Do we have MZ?
Yeah.
21, right? Because we're right here at C, so we don't have to integrate any shear or anything like that. Do we know IZ? So what's IZ for a circle?
It's like 1/4.
That it? Myself, that's it.
So the moment is 21. Y, what's Y? 0.005. And what's IY now, or IZ rather?
Is it?
That's it, right? Is it 1/4 pi r cubed? Yeah.
Is it 1/4 pi r cubed?
It is, 2/4. No, 1/4 pi r.
So it's pi over 4 times 0.005 to the 4th power. You got that? Anybody got that separate piece? The total then should be,
Six,
no, I don't like 6.
672 times 10 to the 6.
I don't like that.
So it'd be 672 megapascals.
No, I don't like that.
I'm getting 78.
What's that?
Yeah.
78.
Well, it'd be
Yeah, no, the number that they have in here is 200.
200 pascals?
200 megapascals.
Six. We'll try it again.
21 times 0.05. Unfortunately, they didn't do pi over 4. They did 0.005 to the 4th power. They just came back with 0.15625 times 10 to the minus 9.
Yeah, I got it. Or
What do you got?
around that. It's like point, I mean, it's like 213.
0.14 times 10 to the 8.
That's it.
Did something wrong the first
So the total is 215.43 megapascals. But here's the other point. Is that, what kind of load is that at point A?
Hey, it's a tension.
Look what I'm doing here.
Right.
Imagine yourself a small bug at that location. I'm doing this. Right? I'm applying force like this.
Oh, yeah, it'd be compression to the top.
I'm squeezing the top, right? So both of these should actually have been negative because they're both compression. So that the stress, remember, the convention is the compression is shown as negative. Okay, that didn't get us very far, but we'll try to, I think we're scheduled to finish, do some more of this next time. I think that's what's on the schedule, so.
I haven't checked and I can't, I just didn't know if you know off the top of my head when the next one was due.
Next Monday.
Oh, it's not due till next Monday.
Yeah, because we have this again on Wednesday, and then there's always the empty class in between when we finish talking about it and when it's due. We'll finish that problem then on Wednesday and then go do another one.
Wake up, boys. Kids
Caleb is today.
He was here.
Yeah, I know, passed her in the hallway an hour ago.